Hello friends, welcome to engineering tutorial. So we'll continue our discussion on thermodynamics. Previously we discussed thermal expansion of solids, in which we discussed linear, surface and volumetric expansion. So there we came across the thermal expansion coefficients alpha, beta, gamma for linear, surface and volumetric expansions respectively. In this video we are going to establish a relationship between the two, a pair of thermal expansion coefficients. First linear and surface, and then linear and volumetric, and then a common relationship. So in this video we are going to derive the relationship between thermal expansion coefficients alpha and beta for linear and surface expansion. So just a quick recap. So we know linear expansion is happening along one dimension when an object, a solid object, is heated. So here, when the subject is heated from an initial temperature Ti to final temperature Tf, it undergoes a increase in length from initial length Li to final length Lf. That increase in length or change in length delta L is given by this. It is directly proportional to the initial length and the change in temperature. The proportionality constant involved is alpha, which is given by this relationship, delta L by Li delta T. It has the following units: Kelvin inverse or degree Celsius inverse. So the final length is given by this: initial length plus increase in length, Li plus delta L, which is equal to Li plus alpha Li delta T. Taking Li common, we get Li into 1 plus alpha delta T. Then comes the surface expansion. Again, let us say we have a sheet which is at an initial temperature Ti, okay, and it is heated to a final temperature Tf. It will undergo an increase in surface area from initial area Ai to final area Af. Here, the change in surface area or increase in surface area delta A is directly proportional to the initial area Ai and the change in temperature. The proportionality constant involved is beta, which is given by this: delta A by Ai delta T, same units as linear expansion coefficients. And the final area is given by Ai plus delta A, which is equal to Ai plus beta Ai delta T. This is taking Ai common. Okay, so we are clear on this. Now we have to establish a relationship between alpha and beta. Again, let us say we take a square sheet. Okay, this is square, just I have tilted it, that's why it looks like a rectangle, but square. So let us say we take a square sheet with initial length Li. So it is Li this way and this way also Li. The initial length is Li. So the initial surface area, it will be Li square. Okay. Now the sheet is heated. The initial temperature is Ti. The sheet is heated and it acquires a final temperature Tf. So as per this relationship of linear expansion, the final length will change as per this: Lf is equal to Li into 1 plus alpha delta T. So the final length is this: Lf is equal to Li into 1 plus alpha delta T. Now the final surface area, again it will be final surface area F, it will be equal to Lf square, square of the final length. So that is equal to Li into 1 plus alpha delta T whole square. So Li square into 1 plus alpha delta T whole square. We have written it in this way. Okay, separately we have done it in separate ways: Li square into 1 plus alpha delta T square. Now we know Li square is equal to Ai. the initial surface area. Okay, the initial surface area AI, Li square is equal to AI. So this can be written as AI into 1 plus alpha delta t whole square. 1 plus alpha delta t whole square, we have used the algebraic expansion a square plus b square plus 2ab. So here it becomes, this is a, that is 1, and b is alpha delta t. So 1 plus alpha square delta t square plus 2 alpha delta t, a square plus b square plus 2ab. Now the value of alpha is very small generally. So the cube terms, the square terms, the higher order terms, they are generally neglected because they are very small. So we can neglect this alpha square delta t square term. We can neglect this term. So it will be equal to AI into 1 plus 2 alpha delta t. Okay, this. So AF is equal to AI into 1 plus 2 alpha delta t. The final area is equal to initial area into 1 plus 2 alpha delta t. Now if you remember, here we derived AF is equal to AI into 1 plus beta delta t in terms of surface expansion coefficient. This is in terms of surface expansion coefficient beta. But here we have got the result in terms of linear expansion coefficient alpha. Here we have got in terms of linear expansion coefficient. This is in terms of surface expansion coefficient beta. So both of them are equal, is the same thing. So on comparing these two equations, everything is the same. AI is the same, 1 plus that is same, delta t is same. Only we have this. Here it is beta, here it is 2 alpha, but they mean the same thing, they're exactly the same thing. The final area, it represents the final area. So it means the surface expansion coefficient beta is twice the linear expansion coefficient alpha. Beta is equal to 2 alpha. Okay, the surface expansion coefficient is twice the linear expansion coefficient. So here is the relationship between surface expansion coefficient beta, okay, surface expansion coefficient beta and linear expansion coefficient alpha. Okay, this beta is equal to 2 alpha, or we can say alpha is equal to beta by 2, this way. So we can also express it as that the linear expansion coefficient is 1/2 of the surface expansion coefficient. Okay, this way also it is correct. So simply we just took first the linear expansion, the final length expression, and we put it here, the surface area of the square sheet. AF is equal to LF square, and then we just expanded it using algebraic expansion formulas. And the important thing here is to neglect this thing, because since alpha, beta, gamma, they are very small, so the higher order terms, the squared, cube terms, the higher power terms, they can be neglected. So it is 1 plus 2 alpha delta t. Okay,